And talk about this next concept about net ionic equations. All right, what we did was we took a molecular equation and we decided what happens when it gets into water. Okay, what happens to the compounds? Are they soluble? Are they insoluble? Do they dissociate into ions or break apart, or do they just dissolve? Moleculars tend to just dissolve and they become so finely distributed in the water you can't individually see them anymore. But they're surrounded by water and they are dissolved. Ionic compounds, on the other hand, have the ability to dissolve in water, be finely distributed, but they do something called dissociate. They actually become their anions floating around, and their anions floating around, surrounded by water rather than them attaching to themselves. There is a case in which they get into water and the attraction between the two ions are so strong that it does not dissolve. And so it is called insoluble, and it's the ions sticking together. And so what we're going to do is we're going to show what is actually happening inside a reaction at the level of the compounds and ions that are there. So what you're going to do is show what's called a net ionic equation. I'll do some examples. So at the bare minimums, you're going to be given reactants because there are a number of different reactions in which you can predict products. You need to go back and look at those, which reactions you need to be able to predict the product. If you have to predict the product, you do that. Then you balance the equation, which is important. Then you label every item as aqueous or solid, liquid, or gas. Okay? And this will tell us what we need to do and how to treat them. Then we write what's called the complete ionic equation by dissociating anything that is aqueous and can dissociate. Once we've done that and have articulated everything that's happening, we take out the spectator ions. We know spectator ions are those that are unchanged from the reactant to the product. They don't change at all. They look exactly the same. And then we write the equation that is left without any of the spectator ions, and that is the net ionic equation, or what's really happening. All right, these are all rules until you actually apply them. Okay? Write the net ionic equation for the reaction of barium nitrate and sodium sulfate. All right, there's a bunch going on here. When you actually start making compounds, I want you to do some scratch work somewhere else to get this done. So when I do barium, Ba, it's a +2 charge because it's an alkaline metal, alkaline earth metal, and it becomes a +2 charge. Nitrate, NO3 -1, or 1 negative. It's something I memorized off a chart. And when I bring these two together, 1 and 1 doesn't balance directly, so then I use the crisscross method. And so I have barium and nitrate, but I have to have 2 of those. The parentheses is very important. It reacts with sodium sulfate. Sodium +1 charge, sulfate 2- charge. Na2SO4, okay? And later I'm going to have to label what it is. All right, in these two cases, I have 2 ionic compounds, so I am going to do a metathesis reaction, and I'm going to switch the cations and anions. So barium 2+, sulfate 2- becomes barium sulfate. Got to label it some way. The other things are sodium +1, nitrate -1, sodium nitrate. I've got to label that somewhere. All right, I've got a equation, still got some things to do with this. All right, all nitrates are soluble except for nothing, so it is aqueous. Sulfates are soluble except for, all right, here's the list. Sulfates down there at the bottom are soluble except for those that have strontium, barium, mercury, or lead. Oops. Is this strontium, barium, mercury, or lead? Nope, so it's aqueous. Sulfates, is this strontium, barium, mercury, or lead? Yes. So all of them are soluble except for soluble becomes insoluble, or a solid, a precipitate. All nitrates are soluble except for nothing, aqueous. All right, I've labeled them, but I have to watch out for the law of conservation of mass. I have 2 sodiums. Put a 2 here, it becomes 2 sodiums, but that also gives me 2 nitrogens. And so here I have 2 nitrogens, and I have 6 oxygens here, plus another 4 is 10. I have 6 oxygens here, plus another 4 is 10, and so I finally balanced it. All right, I have predicted the products. I have balanced it, and I have labeled each one of the compounds as being solid, liquid, gases, or aqueous. An aqueous ionic compound will dissociate. All right, when you do this, you need to ask yourself several questions. Now listen to my litany. All right, does the barium nitrate dissociate? Yes, it does. Okay, what is the cation? Oops, stop. The cation is barium. What is its charge? +2. How many do I have of them? 1. Label it aqueous. Plus, what is the anion? It is nitrate. What is its charge? -1. How many do I have of them? 2. And it is aqueous. Plus, does it dissociate? It is aqueous and it is ionic, so yes. So what is the cation? Sodium. What is its charge? +1. How many do I have of them? 2. And it is aqueous. Okay? Plus, I ask what the ion is. That's the first thing. The ion is sulfate. I ask what its charge is. That's the second thing. -2. I ask how many of them are there. There is 1. And then I have to label it. It's the 4th step. Okay? Yields. Barium sulfate. Does it dissociate? Yes or no? Nope. Drop it down. Sodium nitrate. Does it dissociate? It is an ionic compound and is aqueous, so yes. So what is the cation? Sodium. What is its charge? +2. How many do I have of them? 2. It is aqueous. Plus, what is the cation? Nitrate. What is its charge? -1. How many do I have of them? Be careful. You have 2 of them because you had 2 sodium nitrates, and you must label it. Alrighty. Which are the spectator ions? Which look exactly the same on the reactants and the product side? Sodium. 2 sodiums aqueous, 2 sodiums aqueous. Anything else? What is it? 2 nitrates? 2 nitrates. Anything else? Nope. The net ionic equation is barium +2 plus sulfate -2 yields barium sulfate. Oh, that was aqueous. This was aqueous. And this is solid. That is the net ionic equation. All right. It was not difficult. You didn't even have to multiply and divide. Okay? But it was long. There were a lot of steps. There was an assumption in this. Oh, there's a lot of assumptions. 1, you can make a compound from ions, from the name. Okay? Got to be able to do that. You've got to know all of your ion charges. That's an assumption. All right? You got to be able to balance an equation. All right? And you must be able to use this table. How do you learn this table? What? You memorize it, and how do you memorize this thing? Write it down, right? Write the rules down. But how do you apply it? The TRQs are very, very helpful in this case to be able to think about in a way. Okay? You must know it and know it well enough to use it quickly. Okay? Because eventually you'll be on a time test at a certain point in time. You can't take forever. You take 2 hours to do a 50-minute test, but you got to be able to know this one. Okay? Now, most of the time, net ionic equations are associated with metathesis reactions or special cases of metathesis reactions. And remember, this is a case in which you have one cation switch with the other anion and vice versa. It's a double displacement. For this, there are 3 what are called driving forces, which is the reason why a reaction will occur. I can form a precipitate or a solid. I can form a gas or a weak or non-electrolyte. In this previous example, we formed a solid, a precipitate. You can form a gas, okay, in this case. The last case, you can form a liquid, which is most likely water, or you can form a molecular compound that is aqueous, which most likely is a weak acid. So we can form a weak acid. It is aqueous, but it doesn't dissociate completely. So those are the types of things that will drive the reason why or be the net ionic equation of the reaction. And so in this case, precipitation reactions means insoluble, but we've got to talk about what really insoluble means. It means that not very much can dissolve. Most of it will be a solid when placed into a liquid. And so we get to define that insoluble is 0.01 moles. Moles is an amount that dissolved in every liter at 25 degrees. If it is less than that, then it is considered insoluble. Okay? The other way to think about this is that the attraction between the cation and anion is so strong that water cannot break them apart. And so an example, lead nitrate plus potassium iodide will lead to lead iodide plus potassium nitrate. When you take a look, the net ionic equation is lead 2 plus iodide leads to lead 2 iodide. And that is a precipitation reaction. That is what's actually happening. To form a gas, okay, there are a few reactions that form gases. So the hydrochloric acid plus potassium sulfide creates hydrogen sulfide gas plus potassium chloride. If you take a look at the complete ionic, we can take out the net ion, the spectator ions, and we show that 2 protons plus sulfide ion creates the hydrogen sulfide gas. Smells like rotten eggs. You know you're going to make that. Okay? There is one very special formation that you need to understand. Sometimes you're going to create in a metathesis reaction a compound, a compound that is this, carbonic acid. Okay? In this case, hydrochloric acid plus sodium hydrocarbonate will create sodium chloride and this carbonic acid. Here's the deal. We can predict carbonic acid exists. No one's ever identified or isolated it. Okay? It is so unstable, it will break down into immediately water plus CO2 gas. And so this can be rewritten. Anytime you see this, it can be rewritten as these two because this is what actually is produced. And so the driving force here is both the formation of the gas and the formation of a non-electrolyte. So these reactions go very well because it has 2 driving forces. And that's if ever you see H2CO3 formed, it's never been isolated in real life. To form a weaker non-electrolyte, most often was the formation of water, and so magnesium hydroxide plus hydrochloric acid will lead to magnesium chloride plus water. And when you do the net ionic equation, you can see that we've formed a liquid. The driving force is formation of a liquid in this case. Now, there was one subset of metathesis reactions that I just showed you that we need to know. It is a very special case of metathesis reactions, and that is called a neutralization. Okay? Acids are acidic, bases are basic, and when you react acids and bases, they tend to negate each other or neutralize each other to get to a neutral pH. And so an acid and a base is going to neutralize it. Now, what is a definition of an acid? An acid is those molecules that can donate a proton. A base is one that can accept a proton. A base most likely is the hydroxide. Okay? An acid is an anion that has a cation as a proton. All right, so here is hydrochloric acid and sodium hydroxide, probably the two most famous acids and bases. Will create sodium chloride and water. And so what we have is the net ionic equation for a acid and base reaction is a proton plus a hydroxide will create water. The driving force is to create a non-electrolyte. But what we have done here is an acid and a base is reacting. The spectator ions is what is left over, or is what is the salt. And so a salt, by definition, is the ionic compound that is formed from a neutralization reaction. What's left over? Salts, again, can be very, very general. And so neutralization reactions is a very specific metathesis. I've just switched the anions, but it is an acid and base reacting. So let's take a look at another reaction that we're going to get a net ionic equation. And so we're going to start off with calcium, calcium and hydroxide. Calcium is a +2, hydroxide is a -1. And so when I make the compound, it will look like this. Now, making compounds, do somewhere on another place, do not try to make the compound right there, because you're going to make the compound, you're going to label it, you're going to balance it. If you try to make it with all of the charges there, you will confuse yourself. You have to take an extra step of making the compound so that it is clean when you write the reaction. The next thing is hydrochloric acid, H plus, Cl minus, HCl. Okay, and I'm going to label it. I will then do the metathesis reaction in which an H plus and an OH minus come together to create water. That one I'm going to label liquid all by itself. And then the other two things are calcium and chloride. Calcium 2 plus, chloride 1 minus, so it becomes CaCl2. Okay. And so when we take a look at this, I can see we've got issues. I've got on this side two chlorides. So on the other side, I'm going to put a 2 here to make sure I have 2 chlorides. And if I take a look at calcium, calcium is good, 1 and 1. I now look at 2 hydrogens plus 2 more hydrogens is 4. I will put a 2 in front of here to make 4 hydrogens, which leaves me with 2 oxygens and 2 oxygens. Okay. Now, I've got to decide if they are aqueous, solids, liquids, or gases. I've already labeled the water for you. All right. Now, how do I do this? Well, I have to memorize things. So let's go back. There's a chart. Okay. Oh. All right, we had calcium hydroxide. So right here, all hydroxides are insoluble except for those that contain alkali metals, ammonium, or calcium, strontium, and barium. So that is, it's supposed to be solid except for those, so it is aqueous. So that one is aqueous. Okay. Hydrochloric acid. How do I decide if that is aqueous or not? Okay. In this case, it is a strong acid, so it is aqueous completely, and it will dissociate completely. The other was chlorides. Chlorides, and bromides are all soluble except for those that have silver, mercury, or lead. That is neither silver, mercury, nor lead, so it is aqueous. All right. It's balanced. It's labeled. I predicted the products. All right. 4 questions. What are the questions about this first item? Okay. If it is aqueous and it's ionic, it dissociates. The 4 questions are what? What's the first question? What's the ion? What's the first ion? Calcium. What's the second question? What's its charge plus 2? My third question, how many do I have of them? 1. And the last thing is just labeling it. Plus, what is the ion? Hydroxide. Okay. What is its charge? -1. How many do I have of them? 2. Because of the parentheses, and label it. Plus, it's aqueous. It is a strong acid, so it fully dissociates. So what is the cation? Hydrogen, or the proton. What charge does it have? +1. How many do I have of them? 2. Label it. What is the anion? Chlorine. What is its charge? Negative. How many do I have? 2. And it is aqueous. Does a liquid break apart? Nope. Drop it down. The next thing, does it dissociate? Yes or no? Yes, it is ionic and it's aqueous. What is the cation? Calcium. What is its charge? +2. How many do I have of them? 1. Label it. Plus, what is the anion? Chloride. What is its charge? Negative. How many do I have? 2. And it is aqueous. Now, do you see that the third question is how many are there? If you see Cl2, you don't drop down Cl2. You drop down, what is the anion? Chlorine. -1, and then there are 2 of them. Okay? You have to identify each individual ion. What are the spectator ions? Chlorine, 2 of them. Calcium. Okay? And then I have 2 protons that are aqueous plus 2 hydroxides that are aqueous yields 2 waters. Okay? This could be an acceptable answer, and a lot of times the 2's are left, but you may see it reduced. Both are acceptable answers. You will not see both answers on a multiple choice test. Okay. All right. Got it? Let's go again. Magnesium hydroxide, Mg 2 plus, hydroxide 1 minus. Okay? And so the compound is Mg parentheses OH 2. I'm going to have to label that some way. Plus hydrochloric acid, HCl. Okay. That was a H plus and a Cl minus to create that. Stop. I'm going to have to label that some way. Yields. What are we going to form? What? Magnesium chloride. And you get H as a cation and OH as an anion. What does that form? HOH? H2O. I'm going to label that really quickly as a liquid, because I know that's the only liquid. Magnesium chloride would be MgCl2. I'm going to have to label that. All right. Do you remember your rules for solubility? Someone go back and look at the solubility rules for hydroxides. Does anybody have that? Hydroxides are considered what?
Insoluble, except when containing alkali metals, ammonium, Ca,
Calcium, barium, strontium. Okay. Is this an alkali metal? Magnesium? Is it the ammonium ion? Is it calcium, strontium, and barium? Nope. So I label it what? S. It's a solid. Hydrochloric acid is AQ. And all chlorides are soluble except for what three? Do you remember? Silver, mercury, and lead. So this one is aqueous. All right. Is this balanced? No. What do I have over here? I have 2 chlorines, right? So I'm going to put a 2 in front of this to get chlorines. All right, so I got 2 chlorines, 2 chlorines. That's cool. And now I have 1 magnesium, 1 magnesium. That seems okay. And now I have 2 hydrogens and 2 hydrogens. That's 4. Does this side have 4? No, but if I put a 2 there, I'm good. Stop it. Okay, and now I have 2 oxygens and 2 oxygens. I'm good. All right. 4 questions. After I've determined, does magnesium hydroxide dissociate or break apart? Nope. Drop it down. Okay. Does hydrochloric acid dissociate? It is a acid, but it's a strong acid, so yes, it does. So what is the ion? Hydrogen. What is its charge? Plus. How many do I have of them? 2, and label it. What is the ion? Chlorine. What is its charge? Negative. How many do I have? 2, and it is aqueous. Does water break apart? No. Drop it down. Does magnesium chloride break apart? Does it dissociate? Yes. What is the ion? Magnesium. What is its charge? 2 plus. How many do I have of them? 1. Label it. What is the ion? Chlorine. What is its charge? -1. How many do I have of it? 2. Label it. Are there any spectator ions? Yes, what? Chlorine. 2 chlorines. Are there any others? No. The net ionic equation would be magnesium hydroxide. That is solid. That is not written correctly. 2, that is solid, is dropped in a solution of acid. Okay, and the reactive portion of an acid is an H+, and it will yield 2 waters that are liquid plus a magnesium ion that's floating around aqueous. And that is the net ionic equation for this. Now, do you see that this starts off, it has a solid at the beginning. That's fine. And it has a liquid at the end. That's fine. And so you can have solids in the beginning of the reaction. Not everything has to be aqueous for this reaction to go. But there is a reaction that actually went, and there is only one spectator ion, chloride. Okay? This one actually has some answers already on it, but if I react these two things, write a balanced equation, let's do that. Ooh, I don't even have to decide what's going to happen. Yeah, I don't have to make compounds. This is called acetic acid, the acetate ion and a proton, but I do predict that the H and OH becomes water plus I get barium, that's a 2+. I get acetate, that's a 1-. So the compound is BaC2H3O2. I got 2 of those. Okay, balance this all out. I have to put a 2 in front of this to get 2 acetates. Okay. On this side, I have 2 protons plus 2 more protons makes 4. Put a 2 in here to make 4 protons. And then all of a sudden here, if I take a look at the oxygens, I've got 2 there plus another 4 there. That's 6. 4 there plus another 2 is 6. I'm all balanced. I've got the balanced equation. I have not labeled this. Okay. Interesting. All right. The acetic acid is aqueous, but is this a strong acid? No, it's a weak acid. So even though it dissolves, it is aqueous, it does not dissociate because it is weak. All acetates are aqueous except for nothing. Okay. And hydroxides are all insoluble except for ammonium, alkali metals, calcium, barium, and strontium. This is barium, so this is aqueous. And so I think on the slide they actually give us the answers, in which case the important part we wanted to show you was this. That does not dissociate because it is a weak acid. Okay? The driving force is the formation of liquid water in this reaction. It is also a neutralization reaction because it's an acid plus a base. What showed up there. All right. Kind of curious. Let's look at CHEM-111 real quick. All right, not thermochemistry yet. Solubility rules. So you've got 2 TRQs for this chapter and 1 homework. Okay. All right, number 1 is a net ionic equation. Number 2 is a net ionic equation. Number 3 is a net ionic equation. 4 is a net ionic equation. All right. Oh, and then they're going to classify them. All right, so at this moment in time, you should be able to work, and I would suggest that you try to work 1 through 4 so that you can get down to net ionic equations. All right. And they're going to be asking you to identify some reactions. You're going to need to talk some things before you can finish that section. What's number 5? Ooh. So that compound, let me make it bigger so everybody can see, is acetic acid. All right, it's asking, is it a non-electrolyte, a weak electrolyte, or a strong electrolyte? All right. If it is molecular, it's a non-electrolyte except for, this is molecular, acids. So it's an acid. So an acid is either a weak or a strong electrolyte. How do I decide between these two, strong or weak? For acids, what do you have to know about acids? How many strong acids do I have? 7. Is that one of the 7? No. If it is not one of the 7, then it is a weak. Thank you. You've earned me some points. I like that. Woohoo! All right. So, all right. Not last concept, but next concept. Oxidation reduction. Has anybody remembered oxidation reduction problems in high school? Okay. They can get long, and you have to add water, hydrogen. They can be complex. We're not going to do any of that complexity in this chapter. I'll wait till GChem 2. Okay? What we're really going to do is identify which species becomes oxidized and which species becomes reduced. What happens here is a transfer of an electrons. Okay, remember reactions are only transfer of electrons, but this is a particularly special case in which an entity has electrons, and one entity doesn't have enough electrons, and what's going to happen is one entity is going to steal the electrons away from the other. Okay? And so electrons are going to move directly from one to another. And so we need to know the definition. An oxidation becomes more positive because it loses electrons. A reduction is, at the end, they gain electrons and they become more negative. Okay? Here's what has to happen in a reaction. If something is reduced, something has to be oxidized. I have to be getting the electrons from somewhere if I'm stealing electrons. And so there's a transfer between two entities. Okay? Now, let's talk about oxidation state. We need to identify what oxidation state each of the atoms is in. Now, you kind of learned this already. When chlorine reacts, what charge does it become? Minus what? 1. Okay, because it wants to look like argon, it gains an electron. The oxidation state of chlorine is minus 1. Okay? On the other hand, magnesium, when it becomes a charge, magnesium becomes a charge of plus 2. Its oxidation state is A plus 2. So the oxidation state is the charge that that entity has, okay? And we can predict a lot of them. But sometimes we cannot predict. Okay, so I'm going to give you some rules. An element, the elemental form, has an oxidation state of 0. It is not lost nor gained electrons, so it is 0. Okay, so that's simple. Elements have an oxidation state of 0. Monoatomic ions equal their charge. Whatever the ion is the oxidation state, just like I said. A chlorine is a minus 1, its oxidation state is minus 1. Metals tend to form cations. They are oxidized. Nonmetals tend to gain electrons. They are reduced. Okay. Now we're going to get into some tricky stuff. Whoa. All right. If you have to predict things, all right, oxygen becomes a minus 2 the majority of the time. Okay? There is an exception with peroxide. We see peroxide very rarely, but If you have to predict something, oxygen is most likely going to be a -2. Hydrogen, if it is bound to a metal, becomes a -1. That's very rare. It does happen. But most often, when it's bound to a non-metal, it is a +1. This is what you see most often in general chemistry. Fluorine always has an oxidation number of a -1. Okay? The other halogens, you will predict a -1, okay, most of the time. There are times in which they can become positive, but that's really, really strange. You first assume that they're a -1. Number 4, in a compound, remember the compounds are neutral, so the sum of all oxidation states of every atom in that compound has to add up to be 0. That's going to be important for how we calculate oxidation states. Or the oxidation number, the sum of the oxidation numbers in a polyatomic ion has to equal the charge of that ion. So either, if it's a full compound, has no charge, everything added up has to be 0. And if you have an ion, everything added up has to be equal to the charge of the ion. You write one atom for each element? No. You write one oxidation state for each element. One atom for each element. That's funny. All right, so let's take a look. In the compound hydrogen sulfide, all right, the rule here is the hydrogen is bound to sulfur. So the hydrogen's bound to a nonmetal is a +1, and the sulfur then must be a -2 because of this. If I have hydrogen, 2 of them, and they are +1s, then the sulfur, if this all adds up to 0, has to be a -2 because +1 times 2 is a +2. Sulfur has to be a -2. And so the sum of that equals 0. We're done. S8 has an oxidation state of 0. Why? Why is S8 an oxidation state of 0? Sulfur is found in elemental form as S8. There are others that are diatomic that are found as with a 2, like Cl2. That is the elemental form. That would have an oxidation state of 0. And if it's a metal, you would just say that has an oxidation state of minus, or oxidation state of 0 if it's just the element itself. Okay, for C here, the one that we can predict of everything on that slide is chlorines are a -1. They are halogens. Okay? When I add up everything, it has to be 0. If chlorides are -1, then what does the sulfur have to be in this case? A plus what? A +2. So in this molecule, sulfur is a +2. In molecule number A, sulfur was what? A -2. Oxidation numbers can change depending upon how the molecule is put together. Okay? Usually halogens and cation or alkali metals are the ones that you can predict. We'll start off with this one next time.